做一个桥，就是可能呃用到那个不锈钢，就是双向体的无缝钢管，但是现在好像没有相关的规范，就是这一块儿后面有没有相应的研究补充一下？好像只有焊接不锈钢管的一个规范，就是双向体的。
嗯嗯。您这个问题啊，其实会后这个，到时候我也再给您这个把太钢的，还有这个我们青拓的几位专家的这个联系方式啊，我都再给你推送一下。因为这里面呢，确实在市场上你买可能会这种就是焊管为主啊，焊接管为主，但是确实也有啊不锈钢的无缝管，而且它这个可能成型工艺跟这焊管之间还是有比较大的差异的，有这种材料啊，有这种材料。到时候这个我再给您这个一会儿我接下来单独再给您推荐几个我们国内的这种钢厂，他们都有这种产品啊。
嗯，另外一个我想咨询一下，就是我们不锈钢它表面处理，就是它的表面做法很多嘛，比如说有那个磨砂，还有比如说你做那个镜面，做拉丝，就是这些就是关于它的表面处理有没有相应的规范？
有的也有的，我们的
也
材料
有相应的，
标准里面，对材料标准里
嗯。
面本身就有这种，就是一个是我们的有好多的设计手册啊，包括就是第一次讲的时候，那个 Nancy 教授讲的那个里面的设计手册里面也有不同的材料的这个要求，就是不同材料表面处理的这个点，你想要做成什么样子，对吧？需要怎么做？另外呢，我们自己的国标里面，它是按照什么1号、2号、3号、4号这种编号，也有这么一个这个要求啊。
哦，好的，那我后
嗯
面再再多查阅一下这方面的规
嗯，
范。好，谢
好，
谢谢谢。
好，谢谢两位啊，谢谢两位。因为限于时间呢，我暂时先就是这个请这两位专家先提问，然后后面呢，我们这个整个的交流，下面一段呢是两位国外专家来做这个汇报。在这个汇报之前呢，因为为了便于大家去理解汇报的内容，我先展示一下这个，我再共享一下啊。稍微等我一下，稍微等一下。嗯，这是为了便于大家理解呢，就是腾讯会有一个这个这个直接翻译的这个功能在哪里呢？在我们的这个屏幕的这个下面，在我们这个界面的下面呢有一个应用，你可以点一下应用，点完应用以后呢，这边有一个字幕，你点一下以后，它就会变成开启字幕。就是关闭字幕这个，所以你点它一下它就开了啊，点开了以后呢，这边有一个这个小箭头，你点一下小箭头往上，它会出来一个上面的上拉的这个菜单，上拉菜单以后呢，声音语言你可以写成自动识别英语啊，自动识别英语，这里面呢就是为了防止如果说我说话，它也识别成英语，那就是自动识别啊，中英文它可以自动识别，然后翻译语言呢，叫它直接翻译成简体中文啊，简体中文。这样子就能够在这个讲的过程中，你随时可以看到，翻译的这个结果啊，翻译的这个结果，一会儿大家也设置一下，方便大家在听英语的时候，你英语听力很好，当然没有问题啊。如果这个稍微有点这个难度，你可以打开它，便于您去理解啊，便于您去理解。这是我们的这个就是这个设置这段。下面呢，这个我就把这个共享关掉啊，共享好像就啊，下面我们就请我们的 Nancy 教授和呃Francisco 博士来做我们本期的第二阶段的报告。Let's welcome Professor Nancy and Dr. Francisco to give us a presentation. Can you hear me, Professor Nancy? Oh,
I can hear you.
Okay. Now
Should I
you can
share my
share
screen? Yep.
your screen. Yeah.
Can you see that?
Yes, yes.
Okay, so I just gonna close that. So, hello everyone, and first of all, I'd like to apologize. This presentation is going to be delivered in English. I hope you have all been able to set up your subtitles and have no issues following this presentation. So, well, welcome to this last block of the webinar. This session is called The Resilient Design of Structural Stainless Steel. And this session is going to be delivered by myself, Dr. Baofeng Zheng, and Nancy Baddoo. So here we have the different points we're going to cover in this session. And I will be covering the first 2 points. And I'll talk about how to carry out the fire design of stainless steel structures in accordance with the Eurocodes. And then I'll talk a little bit about some of the work we have done on the seismic design of stainless steel structures. Then I'll hand over to Dr. Baofeng Zheng, who will tell you a little bit more about the seismic design of stainless steel structures, but this time in accordance with the Chinese design code. And then Nancy will finish off the session by saying a few words about the sustainability. Okay, so we're going to start with the fire design of stainless steel structures in accordance with the Eurocodes. There are many applications in which stainless steel is used to ensure adequate fire performance. And in these applications, the selection of stainless steel is often linked to its corrosion-resistant properties as well. So this type of applications would include offshore oil and gas platforms, chemical processing plants, petrochemical plants, or nuclear facilities in which the stainless steel components are also required to have sufficient corrosion resistance in order to be able to withstand the corrosiveness of the environment. Now, because of the volatility of the substances that are handled in this type of applications, it is very important that key part of the structure are able to provide adequate fire resistance. And here we have some examples. So we have blast and fire walls, relief walls, and doors, which you can find, for example, in offshore platforms, and which are used to protect people or critical equipment or key infrastructure from explosions and fires. So we also have accommodation units, walkways, pipe supports and clamps, pressure vessel, storage tanks, etc. So when carrying out the fire design of steel structures in accordance with the Eurocodes, there are the two parts that you need to look at, three parts that you need to look at. So we have Eurocode 0, which tells you which load combination you should use for your fire situation. Then we have Eurocode 1 part 1.2, which tells you how to calculate the thermal action in your structural member. And it also tells you which fire model you should use depending on the application of the structure. And then we have Eurocode 3 part 1.2, which tells you how to calculate the reduced resistance at the elevated temperature. So the calculation of the design load and the load combination for the fire situation is the same for carbon steel and for stainless steel. For the calculation of the thermal actions, the procedure for stainless steel is also the same as for carbon steel, But we will see that there are some differences in the way the temperature increases in stainless steel and carbon steel members. With regard to the calculation of the resistance, the procedure is very similar to the one for carbon steel, but there are some differences that are related to the difference in the material behavior, which I'll describe in the next slides. So as I mentioned, Eurocode 3 Part 1.2 gives the rules for calculating the resistance of steel members, and the main body of these parts focus on carbon steel members, and then all the rules that are specific to stainless steels are given in an annex. Now, in this presentation, I'm only going to focus on the calculation of the resistance in fire. And as I just mentioned, this resistance is a reduced resistance compared to that at ambient temperature, because as the temperature in the steel increases, the steel loses its strength. Now, one thing that you need to be aware of is that even though the strength of the steel is reduced at elevated temperatures, the design loads you need to use to design your members are also lower than those that you have to use for design at ambient temperature. And the reason for this is that the Eurocodes consider a fire to be an accidental situation. And therefore, the load factors that are used to calculate the design loads for the fire situation are lower than the ones that are used for ambient temperature design. So in general, the design loads in a fire situation are going to be less than 70% of the design load that is used at ambient temperature design. So one of the main differences when assessing the fire resistance of stainless steel and carbon steel members is that for carbon steel, it is common practice to use some form of fire protection to ensure that the member is able to meet the required fire duration. And this type of protection might consist of applying an intumescent coating on the surface of the member or boarding the member using fire protection boards. Now, because stainless steel is often used because of its aesthetic and corrosion resistant properties, the member will most likely be unprotected against the fire. And therefore, the fire resistance is going to be mostly conditioned by the ability of the stainless steel to retain its mechanical properties at elevated temperatures. So broadly speaking, the fire verification of steel members, irrespective of whether they are made of carbon steel or stainless steel, consists of two main parts. So first, you have to calculate the temperatures in the member after a certain fire duration, and then you have to calculate the resistance the member is able to retain at that temperature. So to calculate the temperature in the steel member, you can use a finite element thermal analysis, but as a simplification, the Eurocode gives you equations for calculating a single temperature for the entire cross-section of the steel. And you can assume that this is uniformly distributed over the entire cross-section. Now, the Eurocodes give you different heat transfer equations depending on whether the steel section is protected or not. But as I mentioned previously, stainless steel will most likely be unprotected, and therefore the equation that you will have to use to calculate the temperature after a certain fire period is the one that you can see in this slide. Now you can see that there are several parameters that will affect how the heat from the fire is transferred to the steel section. And for example, we have here these parameters, which take into account the shape of the steel section and how it is exposed to the fire. We also have the net heat flux parameter, which takes into account the type of fire you are considering in your design. But the parameters that I want you to pay attention to are those that reflect the thermal properties of the steel. And these are the one I'm showing here. So these material properties are the specific heat capacity, the density, and the surface emissivity of the steel. And as you can see, they will affect the rate at which the temperature of the steel member increases. So in this slide, you can see how these properties compare for stainless steel and carbon steel. So the specific heat capacity tells you how much heat energy per unit mass you have to apply in order to increase the temperature of the section by 1 degree. And in this figure, you can see that the specific heat capacity of stainless steel is very similar to the one for carbon steel. But at around 700 or 750 degrees Celsius, the specific heat capacity of carbon steel shows a peak, which is due to a phase transformation in its microstructure, and this results in the absorption of extra energy. So stainless steel does not show this peak, and therefore you should expect that that the peak in the specific heat capacity of carbon steel will make the temperature of carbon steel to increase lower than that of stainless steel at around 700 or 750 degrees Celsius. Now, with regard to the density, both carbon steel and stainless steel are considered to have the same value, which is 7,850 kilograms per meter cube. Then we have the emissivity, which tells you how effectively a surface emits thermal radiation. But for metals like carbon steel and stainless steel, the surface emissivity also gives you a rough indication of how much thermal radiation is absorbed rather than reflected. So for carbon steel, which has a surface emissivity of 0.7, that means that it will tend to absorb more radiated heat than stainless steel, which has a surface emissivity of 0.4 only. And this means that the temperature of carbon steel will increase faster due to the radiative heat than the temperature of stainless steel. Now, if you take into account all these differences between the thermal properties of stainless steel and carbon steel, you will see that under the same fire conditions, the temperature in a stainless steel section will increase at a lower rate than in a carbon steel section. And that is what you can see in this slide. So this figure is showing the ratio between the temperature evolution of a stainless steel section during a typical fire scenario and the temperature evolution of a carbon steel section of the same geometry and under the same fire conditions. So in the figure here, I'm showing you fire periods of up to 2 hours. And you can see that within these fire periods, the temperature in a stainless steel section can be up to around 20% lower than in a carbon steel section. So as I mentioned before, the fire verification of a steel member requires the determination of the temperature in the member after a certain fire duration, which I just shown you how to calculate. And then once you know the temperature, you can determine how much resistance the member is able to retain. Now, as the temperature in the steel member increases, the member does not only loses its strength, but it will also lose its stiffness. And this is something that happens with both, with carbon steel and stainless steel. But the rate at which the strength and stiffness is lost is different for carbon steel and stainless steel. So here I'm showing you as an example the equations that the Eurocode gives you to calculate the resistance of a column in a fire situation. And you can see that the equations are very similar to the one that I showed you last week for calculating the resistance of a column at ambient temperature. So you have to use a buckling curve to account for global instability of the column. And the formulation of this curve is very similar to the one that you would use during ambient temperature design. Now, the main difference with respect to the ambient temperature design is that in the fire situation, the resistance is based on the mechanical properties of the steel at the elevated temperature. And the way you calculate these properties is by using these retention factors that you can see here. So on the right, you have the definition of these retention factors, and you can see, for example, we have the strength retention factor, which is take into account how the yield strength of the steel reduces with the temperature, and it's giving us the ratio between the yield strength at elevated temperature and the yield strength at ambient temperature. Then we also have the stiffness retention factor, which accounts for the reduction in the elastic modulus, and is giving us the ratio between the elastic modulus at elevated temperature and the elastic modulus at ambient temperature. Now, these retention factors have been determined from tests, and there has been a lot of work recently in Europe to determine these retention factors for stainless steel. Now, one thing that is important to consider here is that the yield strength at elevated temperatures and at ambient temperature are not defined in the same way. So for ambient temperature design, the yield strength is taken as the 0.2% proof strength. But for the fire design, because the fire is considered to be an accidental situation, it is considered acceptable that the structure would deform more than what we'd consider to be acceptable under ambient temperature design. And because of this, the yield strength for the fire situation is taken as the strength at a 2% strain. Now, this is the same for carbon steel and stainless steel. But for carbon steel, if you look at the strength at a 2% strain at ambient temperature, you will see that it is the same as the yield strength because of the yield plateau of carbon steel. Now, for stainless steel, because of its significant strength hardening, at ambient temperature, the strength at 2% strain is going to be higher than the strength at the 0.2% proof strength. Which means that by defining the yield strength at elevated temperatures as the strength at 2% strain, you will be able to take advantage of the strength hardening. So the way in which steel loses strength is very alloy dependent, but the reduction in stiffness is more similar for all the different stainless steel alloys. So in order to take advantage of the good retention capabilities of some stainless steel alloys, the Eurocodes classify all the stainless steel alloys into 7 different groups, which you can see in this slide. Now here I'm showing you how stainless steel and carbon steel retain their stiffness at elevated temperatures. And all the stainless steel alloys are considered to have the same stiffness retention at elevated temperatures, which is given by the red curve. And you can see from this figure that stainless steel is able to retain a larger proportion of its stiffness compared to carbon steel. And this has a beneficial effect on the buckling performance of stainless steel at elevated temperatures, which, as I explained last week, is dependent on the elastic modulus. Now here I'm comparing the strength retention of the stainless steel alloys that belong to each of the 7 groups considered in the Eurocode against the strength retention for carbon steel. And also in the figure on the right, I'm showing you the strength retention of only the stainless steel alloys that are covered in the Chinese standard. So you can see that the strength retention can vary significantly depending on the stainless steel alloy. And you can also see that the strength retention factor for stainless steel can be larger than 1. And this is because of the way the yield strength at elevated temperatures is defined, which, as I mentioned before, is taken as the strength at a 2% strain. You can also see that some stainless steel alloys start losing strength a bit faster than carbon steel, but they are generally better at retaining their strength at temperatures that are greater than 500 degrees Celsius. Okay, so here I have the main takeaways from this part of the presentation. So first, stainless steel is most likely to be used unprotected. And also the fire design of stainless steel is similar to that of carbon steel. The only difference is that you have to take into consideration the specific thermal properties of stainless steel. I have also shown you that the temperatures in a stainless steel member increase slower than in a carbon steel member. And stainless steel is also able to retain its resistance better than carbon steel, which tells you that stainless steel performs better under a fire situation than carbon steel. Now, you need to be aware that stainless steel is most likely to be used unprotected. Because of this, you should not expect to replace the use of carbon steel for stainless steel purely based on its to support the use of stainless steel, like, for example, aesthetic reasons or corrosion resistance. Okay, now I'll tell you about this work we have done on the seismic design of stainless steel structures, which was focused on the way the US carry out the seismic design. So at the moment, neither Europe nor the US provide any formal guidance on the seismic design of stainless steel structures. And this means that designers that need to carry out the seismic design of a stainless steel structure have to make their own assumptions, which in some cases might be conservative, but in other situations could be potentially unsafe as well. So as part of an initial effort toward the development of more specific design rules for stainless steel structures in the US, myself, Nancy, and other American colleagues wrote a paper which provide simplified and general recommendations on how the rules that are given in the American design code should be modified in order to make them applicable to stainless steel structures. So these recommendations only focus on stainless steel structures that are made of austenitic or duplex stainless steel. And in the next few slides, I'm going to briefly outline some of these recommendations. Now, bear in mind that these recommendations are based on the way the American design codes carry out the seismic design of stainless steel structures. So they might not be directly applicable to the way in which seismic design is carried out in China. So here you can see the full stress strain characteristic of a typical austenitic and duplex stainless steel. And these are the same stress strain curve I showed you last week. And you can see how the stainless steel curves compare to the stress strain curve of carbon steel. So as we discussed last week, the elongation at fracture of stainless steel is similar or even better than that of carbon steel. And stainless steel shows significantly more strain hardening than carbon steel. And this occurs gradually from the onset of yielding without any yield plateau. In addition to this, stainless steel also shows equivalent or better toughness than carbon steel, especially the austenitic stainless steels. And welded joints that are made of stainless steel also show good strength, which is all good for seismic design. So in seismic design, a design methodology that is often used is called capacity-based design. And what this means is that the structure is designed so that only certain part of the structure yield, while other parts remain elastic. So the structure is basically able to resist the earthquake through the energy dissipation of the yielding components, which will deform inelastically. Now, to ensure that the structural elements that are meant to remain elastic, what you have to do is to design them so that they can resist, while remaining elastic, the maximum inelastic resistance the energy dissipating members are able to develop. And because of this, it is very important to be able to take into account the strength hardening of stainless steel when doing capacity-based design. Here you can see how the hysteretic behavior of austenitic stainless steels compared to that of carbon steel. So austenitic stainless steel shows more cyclic hardening than carbon steel. And you can see that in this figure by comparing the cyclic curve against the monotonic curve. So the difference between these two curves is basically what we call the cyclic hardening. And you can see how it is larger than what you will get for carbon steel. So when carbon steel is cyclically loaded beyond its yield strength increases with each cycle, but after a few cycles, it stabilizes. Now, for austenitic stainless steel, this doesn't occur, and their strength continues to increase with each cycle, which is why you end up having a larger cyclic hardening than for carbon steel. Now, for duplex stainless steel, the behavior is something in between that of carbon steel and austenitic stainless steel. So being able to predict this cyclic hardening behavior is also very important when doing capacity-based design. Another important thing to consider when doing capacity-based design is the overstrength of the steel. So this is basically the difference between the nominal strength of the steel you use in design and the actual strength of the steel. The ratio between the actual yield strength of the steel and the nominal value is known as the overstrength factor. And for stainless steel, this is not going to be the same as for carbon steel. So in this figure, you can see the overstrength values we measure for a large number of austenitic and duplex stainless steel alloys. And you can see that the overstrength factor is generally larger than 1, which is what you would expect, because you wouldn't like the actual strength of the steel to be lower than the value you use in design. Now, for seismic design, you also wouldn't like the actual strength of the steel to be too much higher than the nominal strength, because that could affect the way the structure dissipates energy. So we estimated the overstrength factor for austenitic and duplex stainless steel that should be used in seismic design, and the values we're proposing based on the data we collected are 1.6 for austenitic stainless steel and 1.5 for duplex stainless steel. Now, if you compare these values with the ones that are used for carbon steel in the US, which range between 1.1 and 1.6, you can see that they are on the upper end of the range. So in order to determine the expected strength of the energy dissipating members that you need to use when carrying out the capacity-based design of a stainless steel structure, you will need to consider the overstrength factor, the strength hardening, and also the cyclic hardening behavior of the material. Now, if you define the expected strength factor R sub y as the ratio between the actual strength of the steel material of the material during an earthquake divided by the nominal yield strength, you can estimate the value of the RY factor for stainless steel by adding the contribution of the overstrength factor, strength hardening factor, and cyclic hardening factors, which is what you can see in this slide. And we have estimated that the expected strength factor R sub y for austenitic stainless steel should be taken as 3.1, and for duplex stainless steel, it should be taken as 2.6. Another important aspect of seismic design is the selection of the seismic design parameters. And these seismic design parameters are needed when the internal forces in the structure due to the seismic action are obtained from an elastic analysis. So when this is the case, the internal forces and displacements in the structures are obtained assuming that the structure behaves elastically, and then the seismic design parameters are used to modify these forces and displacement to account for the inelastic behavior of the structure. So here I'm showing you the seismic design parameters that are used in the US. The first one is the response modification factor R. And this factor is used to reduce the elastic forces that are obtained from the analysis. And the factor depends on the ductility of the system, which in turn depends on the type of structure and the overall strength of the system. Now, even though the overall strength of the system can be expected to be greater for a stainless steel structure because of the material overstrength, the strength hardening, and the cyclic hardening, our recommendation is to take the R factor to be the same as for carbon steel structures. So this is a conservative recommendation. Then we have the system overstrength factor, which tells you how much larger the strength of the structure is compared to the force level that is used in design. And as I have just mentioned, this factor can be expected to be larger for stainless steel because of the larger material overstrength, larger strength hardening, and also larger cyclic hardening. So taking this into account, we recommend this factor to be taken as 1.5 times the system overstrength factor for carbon steel, but no greater than the R factor. Now, the last factor we have is the deformation amplification factor, which tells you how much the structure is likely to actually sway or deform during an earthquake compared to the elastic sway or elastic deformation that is obtained from an elastic analysis. So we are also recommending to take this factor as 1.5 times the deformation amplification factor for carbon steel, but again, no greater than the R factor. Okay, so that is what I wanted to tell you. Now I'll hand over to Dr. Baofeng Zheng, who will tell you more about the seismic design of stainless steel structures, but this time in accordance with the Chinese design code.
好，谢谢。Could you close your screen? 哦 ，OK。好，各位专家，然后我把这个刚才呢听了那个Francisco 博士对这个欧洲规范在美国规范的这个抗震啊做了一些介绍，应该是做了很细致的工作。我呢简单的花10分钟以内的时间吧，把这个中国的不锈钢规范的这个抗震这一块是怎么来考虑的，来给大家展示一下啊。等我一下。好，这个目前呢，屏幕展示的呢，就是CCS 410修订版里面的主要的这个抗震这边的思路。这里呢，因为我们国家的这个钢结构设计标准啊，在2017版的时候给出了不锈钢结构抗震性能化设计的方法设计方法。在此之前呢，大家都采用的是抗规理的做法来去做这个事情。刚才那个 Francisco 博士呢，他在讲的时候，实际上讲的是我们国家对应的抗震性能化的设计的这个部分的内容。因为在欧洲，在美国，他用的都是中震设计，中震设计。我们国家是三阶段的设计，叫小震的这个小震下去计算，然后中震下做了一定的这个就是变形可控，然后这个或者还有一定的变形可控这样来去做的。所以在这个50017的2017版里面呢，引入了 钢结构的抗震性能化的方法。总体来说，这方法是非常的先进的啊，先进的这个，所以我们不锈钢结构的这边呢也是2条路，一条路呢，它可以按照抗规严格的要求所有构件的抗侧力构件的这个构造设计要求，另外一个方面呢，也可以走50017的这个性能化设计的路线啊，性能化设计路线，这里面呢有些参数啊，因为之前这个 PPT 我没有认真的去核对前后2个 PPT，可能有些参数的这个叫符号有点不太一样啊，符号有点不太一样。这个呢，相当于刚才那个报告里的 R，就是这个R1/1啊折减系数，就是中震算下来的这个结构的内力要除以多少来去做设计啊，做验算啊，它那是除以多少，因为那是打1的，咱这个地方呢，性能系数这个 behavior factor 就是要乘上0.35，乘上0.7，乘上1.0。这样来做设计，这是我们的性能化里面的路线，也就是说，它允许你的结构是纯弹性的中震弹性，那就在中震下，你就按照1.0的地震内力去做设计，能做下来那就可以了啊。也可以允许你有很大的延性，这个因为结构进入非线性阶段以后，它的地震作用跟弹性阶段的如果是纯弹性的结构，它是完全不一样的，所以我们这个性能水准3是乘了一个0.35，也就是0.35去乘上中震计算下来的那个地震作用，这个值呢就相当于我们的小震了，等于我们小震这个地震力的水平，然后去做设计，但这时候就要求它的构造要求就比较高，整个结构的延性水准就比较高啊。中间这一档呢是这个就是两边都可以就是这个兼顾的这么一个水准啊，这么一个水准，这就是我们国家的两种方法，一种呢按照这个50011的这个抗规去做，计算构造全部按照这个去做。另外呢，也可以按照这个我们钢标里的性能化的方法，把这个性能等级，我们有3个等级啊。当然，欧洲啊跟这个美国他们的性能等级的，我也没看到它最新的版本。正常情况，它不同的结构形式啊，也是给了不同结构形式对应的这个就是这个性能系数啊，这个性能系数，这是一个方面啊，一个方面，所以我们应该是脱身于50017啊，我们的钢结构设计标准，然后呢，基本的原则50011的这个基本原则内力计算，这个我们还是要去遵守啊，去遵守这个点上啊，这是我们的设计思路。真正的实际上这个性能化设计的实施啊，是我个人也做过1、2次，就是这个不锈钢试算啊，这个结构试算的其实还是比较就是这个稍微变麻烦一点啊，肯定是要有一个迭代的过程。你先假定这个性能系数，假定性能系数呢，然后你去做中震下的验算，可能这个你的设定的性能系数0.35跟你真实的性能系数之间还不完全一致啊，还不完全一致。其实它的总的要求呢是要求你耗能区出现缩影角的区域，这些区域的性能系数要达到这个值，其他地方你的结构的内力都按照这个比较高的这个内力水准去做，就是它不能坏啊，它不能坏，这就是后面那个超强的这个问题，其他地方不能坏。这个地方我认为我设定缩影角的这个区域，它就要跟我的这个耗能这个这个性能系数要接近，所以这需要一个迭代啊，这需要一个迭代的这个过程，才能够让这个设计性能化的这个满足。这个呢，今天因为时间也是非常短，所以这个整个流程。也就是一次性可能也不能完全的讲得清楚啊，讲清楚。有了这个性能系数啊，有了性能系数以后，其实还离着这个做设计还有很长的路，因为你要保证你的耗能区、塑性耗能区的性能系数是我们的设定的值，但是还有一些不耗能的区域，那些其他区域在这个整个的执行过程中，就是这个计算过程中，它都是不能坏的。怎么让它保证不能坏？就是刚才那个弗朗西斯科博士在介绍的时候，它里面有一个超强系数，那个超强系数呢，取值呢，这个做来做去呢是这个比较大，它比碳钢的要大，因为这个材料它后期强化的是比较厉害的，所以它是有循环强化，再加上本身的这个去强比的这个问题，所以它值比较高，最终碳算出来的是碳钢的1.5倍。 是碳钢的1.5倍。那这个呢，我们自己在做中国规范的时候，其实也做过这个探讨。但这个探讨呢，如果我把这个，就比如说我们的连接系数、超强系数，真的取成了碳钢的1.5倍这个值，实际上会给你的连接，会给你的这个就是除了你的，就是你有耗能区，有这个弹性区，你的弹性区就要做的非常的夯实了非常的夯实了。这个可能也有不同的这个，因为现在这个都不是特别成熟，所以我们这边呢，这个先让它这能直线下去。欧洲、美国规范也在变也在处于这个不停的修改的阶段。1.5倍这个值再乘上我们碳钢里面那个超强系数，它这样子下来呢，我的这个连接节点可能。能就是概念上是对的，但是真正的要实施到这个点上，难度是非常大的。所以我们呢，考虑到实施的可能性，包括连接的配套的这个可能性呢，对这个超强系数、连接系数这些类的东西，保证弹性的状态这个系数，都做了提高。那比我们碳钢的，比如多原来是1.4，我们提高1.5，或者说原来1.45提高了1.5。就提高了这个0.5或0.15这个度，这个度的主要的考虑呢，还是在于，就是我们觉得这个弹性的状态，就是让这个耗能区域和非耗能区域，那个非耗能区域就处在我们设计的那个弹性状态下，这边就已经考虑如此多的强化了，它也不完全是一个就是不锈钢结构可能是最理想的状态，就是大家都会强化，不仅仅是。你的耗能区会强化，你的弹性区也会随着你的荷载的增大也会强化。那如何保证它们会坏呢？那就是你在耗能区的这个力，确实你有了一个1.5倍或者说1.25倍的提升，你确能够保证这个，就是在你出现塑形角的时候，其他地方还不那么坏这个不能坏的不那么厉害。所以这是我们的一个现在也不是完全成熟的这么一个做法。因为它不成熟所以这个东西就是。对，这还没到呢，就是这个弄完了以后呢，因为盐性高的这个区域，特别是我们的这个，比如说我取0.35，那我的塑形耗能区就要求很高了，这个截面就是不能够再发生局部区或者是任何的其他的这个就要充分的发展它的塑性，所以这时候呢，跟着我们的前面的截面分类就挂钩，你的0.35的这个这个性能，我们叫性能系数。你就要求你的耗能区的这个构建必须达到 SS1的这个就是盐性等级，也就是说这个地方你性能要求高，所以我的盐性等级，你的宽厚比我就要求严格一点让你这个地方能达到。如果你是1.0性能系数取1.0，就是说结构是弹性的结构在中正上都是弹性的，那可以完全硬扛，用 SS3这个可以允许它用这个甚至做有效宽度计算的这种薄柔截面来扛住中正的这个内力。这个因为我们王立军大师也给我们了很多的指导，就是在这些我做的一些是轻型的结构上，可能这样做会就是特别轻钢厂房或者类似的这种结构或低多层的结构，它地震作用不起控制作用你就算到中正，它也能算过去。这个时候就可以把这个性能系数取得高一点，0.7。这个1.0，地震力就算是中正来算也能算过这样子就可以可能更经济一点这是这个整个东西的一些理念。因为这个东西我们说这个不行，这个因为太不成熟了这个系数呢取值确实有一定的依据，但是也不能完全还不完全的，所以呢我们这边呢一共做过304的框架的低轴往复，205的这个典型的奥氏体不锈钢和典型的碳钢，典型的这个双向钢的这个低轴往复的实验，就是框架低轴往复。然后在北工大，在这个其他的高校也做过其他连接形式的这个实验这个实验，总体做下来呢，这个应该说，因为这个不锈钢材料它这个就是屈服后强化还是很厉害的，这个屈服后的强化呢会延缓结构发生塑性变形的这个的，所以你在现场你会看到不锈钢这个变形同样推到了同一个水平位，这截面都是一样的截面这个材料强度也差不多一样345的355的跟304差不多，所以你会发现这个不锈钢这个材料的这个变形不是特别的大，而这个碳钢这个变形就非常的明显，而且都过了极值，然后进入了这个下降的阶段，不锈钢的这个曲线一直向上涨，也就是说它的可能会残余变形会小一些 结构的这个无论是局部的参与变形还是整体参与变形都会小一些。就是按照这个我们加强和不加强这个观点来做呢，就是加强的幅度不要那么大的情况下，特别是连接啊，我们这个端板连接这个地方，如果你要增加1.5倍，那这个螺栓就得原来8颗变到10颗，变到更多颗。实际做下来这个端板连接它没坏啊，它没坏，所以我们认为，至少在现在这个阶段，在大家都还没有完全搞清楚这个东西阶段，通过2个实验还有一个双向钢的这个实验来去做这个点呢，连接没坏，常规设计的这个连接没有坏啊，我们认为这个连接系数还是有一定的这个可信度的。但是这里面也有一些就是实验里不是一帆风顺的。这个双向钢呢，在焊接了以后呢，因为这个双向的比例发生了一点点变化，可能会导致你的这个材料的粘性会降低。所以在焊接的时候还是要特别的注意的啊，特别注意的。同时我们也按照这个刚才说的这个美国的方法，美国其实有一个飞马695的方法去验算你这个结构到底是就整体结构去验算它能不能满足规范里的这个指标的要求，就去做验算。就是限值是这个值，然后其他值如果比它高，那就是满足啊。当到 SS3 的时候，确实会有一些会降低但是呢还能守住底线。这是我们目前的这个做法啊。这是我们的中国规范的一些介绍啊。我的这个介绍部分呢，就是关于中国规范，大概10分钟左右啊，就到这里啊。Hello, Nancy.
Hello, Baofeng. Hello,
嗯
everyone. I will now share my screen. Can you see my screen?
Yes, yes.
So, good evening. Thank you for staying towards the end of our webinar series. And I am going to finish with a few slides on the topic of sustainability, and then I will summarize things. Firstly, stainless steel is highly durable. Structures made of stainless steel, well, they can last for many, many decades, even in aggressive environments, without significant degradation. I've shown on this slide some examples of structures dating back to 1929 in London. Of course, Stonecutters Bridge, that is now 17 years old. And the Helix Bridge is a similar age. And the fact that stainless steel can last many decades reduces the need for repair, replacement, and the associated material consumption over time, which lowers environmental impact. With coated steel, you do need to carry out regular painting and application of protective treatments. But with stainless steel, you don't need to do this. And the savings in maintenance intervention, it reduces waste, emissions, and of course, disruption. So although for stainless steel, when it's produced, the embodied carbon will be higher, the fact that you have reduced maintenance, longer lifespan, and minimal replacement often results in lower whole life carbon compared with alternative materials. Stainless steel is 100% recyclable with no loss of quality. New stainless steels, they typically contain a high proportion of recycled material, often 60% or more. And this supports circular economy principles and reduces demand for virgin resources. statistics gathered have shown that in the building and infrastructure industries, about 92% of stainless steel is collected for recycling at end of life. You may ask, where is the data that supports this? And I'm happy to tell you that environmental data for stainless steel is available. So if you are carrying out whole building life cycle assessments, there is data to support your analysis. If you go to the World Stainless website, and I've put the URL on this page, on this slide, there is data you need for life cycle inventory and analysis, and there is also data on the production of stainless steel, and increasingly these days stainless steel producers are publishing environmental product declarations, and I think that's the same in China as it is in other parts of the world. And this can give you the details of the actual material that you're specifying in terms of environmental impact. And some stainless steel producers are now publishing EPDs for different product forms and different alloys. So it's quite a lot of detail now available. In closing, I have some comments to make to summarize the message of the last 4 talks we have given on structural stainless steel. Stainless steel is a family of corrosion-resistant and resilient steels. They have a range of corrosion resistance and mechanical properties, also a range of toughness, and they are suitable and cost-effective to use in many applications, but not all. The applications where you might choose stainless steel are very corrosive environments, by the sea, for example, or where you use de-icing salts. In those structures that have a very long life, or where maintenance is difficult, expensive, or impossible, and also for architectural structures where the exposed metallic surface finish is very important. In this series of talks, we've explained how the structural response differs to carbon steel in some aspects only. Sometimes you can use the same rules for carbon steel, but when you have instability, buckling, and deflection, you should be careful to use appropriate rules for stainless steel. And then finally, we have talked about the different design codes and guidance that is available for structural engineers, designers, architects, and also fabricators working with structural stainless steel. So most importantly for you, the Chinese standard CECS 410 is available, and shortly a new version will be published. If you're working on projects using American standards, then it's AISC 370 you need, the specification for structural stainless steel. And if you're working on a project using Eurocodes, then it's EN 9093-14. So that completes what we have planned to say, and I'm going to hand over to you if you would like to ask us any questions.
Okay, thank you. Sorry.
I'll stop
Could
sharing.
you, yeah, could you stop your, yes, and open your camera? Yeah.
You need to give me permission.
Yes.
Okay.
Okay. During the presentation that I received two questions. First one from the Changsha Broad Group. They have a question about residential building. So could you tell us any residential building in the could you tell us something about the residential building in the UK or US? And are
Sorry,
there any new grade of design method used for residential building? 住宅.
I'm sorry, I don't. What is that word? Are there any design?
I will put it in
Put it in the
the
chat. Yeah.
message.
Residential buildings, Nancy.
Oh,
Yeah,
residential
yes,
yes, of course, because that is the
Sorry.
market. That's interesting. I do not know of any current projects in the US nor Europe where they're using structural stainless steel in modular construction for the residential market. No, I know that this has been applied in China with some success, a very interesting project and an exemplar really, but we do not have anything similar to that. Because my experience is that for stainless steel, it's really for environments that are difficult, corrosive, and in residential projects, your structural members are inside, they are protected from the environment. So you would use stainless steel, say, for a balcony where you have external stainless steel. If you were located by the sea, there are many residential high-rise buildings with balconies, so that would be an application. But for internal stainless steel, sorry, for internal structures, no, I don't know any residential projects.
In China, the Changsha Broad Group have built a lot of buildings using pure stainless steel. All of the materials stainless steel.
That's impressive.
So welcome to China. Welcome to Changsha to have a look. So the second question，这个刚才我简单解释一下，就是Nancy就是说这个可能李总刚才可能是这个室内的环境啊，可能他无法理解我们这边就如此长寿命的这个结构的需求，对吧？如果是仅仅做一个传统的这种结构呢，认为这个50年的周期内，这个不锈钢可能它的耐腐蚀性足够来室内的用不着这么高级的材料啊，但是如果从我们长寿命这个角度，我觉得远大公司做的还是非常厉害，大概这点。还有一个问题来自于我们中野的吴总啊，那个 question so the next question from the Professor Wu 吴耀华吴总，然后his question about the boat. Are there any high strength boats, 10.9 or 12.9 grade boats in Europe or the US?
They are less widely available, but they are manufactured by a company called Bumax. Bumax, perhaps you know them, and they do specialist bolts, high strength bolts. The duplex property class 100, so that has a tensile strength of 100 megapascals. Beyond that, I think probably Bumax do one step higher, but it's just difficult getting large quantities for projects.
Yes. 好，我简单的把这个刚才 Nancy 教授这个翻译呢，跟我们吴总汇报一下。就现在欧洲刚才说的有个公司叫 Bumax， 它那个生产这种100级的，就是1000兆帕的这个螺栓，它是有的，当然是有的。但是这个现在的标准呢，或者可能欧洲的标准也应该是在发展中，因为用量比较小，可能它也不太容易就是一步到位到那么高的程度。12.9应该目前可能还没有见到。是这么。我再问一下，看看有没有什么这个标准。Are there any guide for the high strength boat? Design guide for the high strength boat?
Yes, we have written an American Institute of Steel Construction guide covering all stainless steel bolting. And there is a product standard, ISO 3506, which I think is equivalent to your own product standard. It is very important that the market grows for high-strength stainless steel bolts. There is demand, but the supply is not there yet.
Thank you. 就这个相关的规范，可能国外也比较少啊，也比较少。这个 Bumax 这个公司的这个产品呢，我们国内我也买过几次啊，就是进口的这个螺栓买过几次，也价格也非常贵啊，价格非常。我们现在就是也是在国内也在编这本规范呢，就是要把这个价格啊，还有这个产品啊，要成熟一下啊，价格降低下来啊。Okay. Any questions from our audience? I can. 现在大家可以这个直接开麦啊，可以讲哦，这里有一位啊。你可以讲了，这个举手的这个 BEEZ 的这个您这个话筒我已经打开了。BEEZEESS， 这个还有另外一位也要打开话筒，现在应该是可以自主解开话筒了。我把这个权限已经放开了，可以自主的解开话筒。您可以听到吗？这位，您说
，OK，我有2个问题，可能想问一下 Francisco。
你直接用英语，如果能用英语，直接用英语给他说。
OK， 好的。
So the question
Hey,
come to Francisco. Yeah.
Hey, Dr. Francisco. Thank you for the presentation. I have 2 questions. The first one is related to your previous one in the last week. I recalled that you mentioned for stainless connections, we typically don't use galvanized connections there because there may be some issue. But from my limited knowledge, I think, like, for example, for reinforcement concrete, we typically, like, for the durability concern, we typically like use a galvanized rebar in the place where there may be like a high exposures. So I'm just wondering if you may explain a little bit more why galvanized connection is not preferred for stainless steel connection. Thank you.
Okay, so regarding the use of galvanized steel for the reinforcement, I'm assuming that this implies the reinforcement is inside the concrete, and in this case, it is protected by the concrete. So in this type of situations, you wouldn't have any issue of galvanic corrosion, which is what I was referring during my previous session when I was mentioning that you shouldn't use galvanized bolt to connect stainless steel members. The concern there is the issue with potential galvanic corrosion. Now, if you have reinforcement is protected by the concrete, this issue wouldn't happen. So it is possible to have galvanized reinforcement and also ungalvanized reinforcement and use that near stainless steel, there wouldn't be any issue with galvanic corrosion there.
I see. Yeah, thank you. And the second one is when you talk about the fire performance of the stainless steel today, you showed that the fire how to say the Young's modulus reduction and the strength reduction for the stainless steel seems like compared to the typical carbon steel, it's performed better. And it seems like carbon steel typically will be used with either fireproofing or intumescent, those kind of stuff. So just from my curiosity, since stainless steel is typically used exposed, so if we compare exposed stainless steel and a typical carbon steel with typical intumescent painted at the outside, so how the performance looks like compared to each other, and how the cost looks like compared to each other?
Yes, so that's a very good question. In my presentation, I was comparing unexposed stainless steel with unexposed carbon steel. And what I was trying to show is that stainless steel performs better under fire than carbon steel. But yes, one of the important things that you need to consider is that stainless steel is going to be used most likely unexposed, and carbon steel could be most likely will be used exposed. So in those circumstances, carbon steel will perform better than stainless steel, and that's kind of like the point I was trying to make in my last slide, where I was saying that you should not expect to replace the use of carbon steel purely based on fire, on the fire performance criterion, because if you protect carbon steel, you will get significantly better fire performance than stainless steel. So so yeah, the idea is not to suggest that you can replace carbon steel with stainless steel purely based on fire performance, but to highlight that stainless steel performs better purely if you consider that there is no fire protection.
Thank you. I think another follow-up is like probably like a selection of stainless steel or carbon steel with intumescent at the outside is more like maybe architecture perspective or owners like a selection. But from the cost perspective, may I ask, like, if we paint the intumescent at the outside of the carbon steel, or we directly use stainless steel, which one may be relatively more costly?
I would think that protecting carbon steel with intumescent coating will be cheaper than using stainless steel. So again, the intention in my presentation was not to suggest that you should try to use stainless steel as opposed to carbon steel purely based on fire performance.
Yeah, I got it. Yeah, thank you very much.
好，
No
谢
problem.
谢
Thank
这
you.
位好，谢谢。看看还有那个专家有对这个讲的内容啊，我刚才您可以开话筒了，就是这位我叫不上名字了，您可以直接开话筒。
Can you?
啊，对，哎。
Can you hear me?
可以。你这个
Yes.
I am doing the how can I say, the topic of my master degree about the concrete fused stainless steel, the fire performance of concrete fused stainless steel tubular columns, but I have to use the finite element model. But the finite element model that I'm doing right now give the so much error when I increase the load ratio. So but when I see the constitutive model of my concrete, I see that I didn't account the confinement of the stainless steel when the temperature is higher, but I see the the material properties of stainless steel in higher temperature, I see that the stainless steel can retain the strength when the temperature is high. So should I account the confinement of the stainless steel when the temperature is high or not? The constitutive model of the concrete, sorry.
Is the question, I guess the question is to me, or?
Yes, can you answer it? You could refer to the new equations in Eurocode 3.1.2 or Eurocode 3.1.14.
I think this question is very specific. Should you consider confinement provided by steel? Well, I would say yes, but depend on the temperature you're looking at. But in the same way, I would also consider it if I'm studying a carbon steel concrete filled tube. But it will all depend on the temperature you're looking at.
Because sorry, because since the beginning of the temperature, the stainless steel is the strength of the stainless steel is quite reduced a little bit, right? But then when the temperature is higher, it can retain more. So I am just deciding what should I account for the confinement or not.
And is this confinement, how is this confinement accounted for? Do you simply increase the strength of the steel of the concrete?
Yes, to increase the compressive strength of the concrete.
In that case, I wouldn't. I'm not entirely sure. What I would do is I would look at the research literature and see how others are considering this confinement, whether they apply a reduction factor or something.
Yes, it's quite a little bit specific. So,
yes, very specific.
I'm sorry.
已经很好。
Thank you so much.
It's okay, thank you.
谢谢。这个同学，我不知道您在或者那个专家您在哪边工作，您反正会后您肯定能联系到我，联系到我以后呢，我再给您这个就是把这个2个专家的联系方式再建立一下，您可能能获得更好的答案啊。
Can I share my screen?
Okay.
I think I can. Yes.
Yeah.
I just wanted to take the chance to remind people that recordings of these talks and PDFs of the slides will be available in a few days' time at these locations.
Yeah, and I will send the link to the WeChat. Yeah, so everybody can see it.
Perfect. Okay.
好，看各位专家还有什么问题？因为这个时间确实也不早了。最后一个问题吧，最后一个问题，看看有人举手啊。如果您要那个，你只要是打个举手，或者直接开麦也可以。
So I think perhaps if we haven't got any more questions, is it time to end? Or we have.
Yes. Yeah. 好，非常感谢thanks Professor Nancy and Dr. Francisco。非常感谢这个我们这个各位专家能坚持到最后2个多小时的报告，看了一下这个大家都这个都很集中精力听，后面这几个问题也都非常的这个专业的这个问题。应该如果大家有更多的这个就是无论是在这工作学习过程中有各种的这个疑问，都可以应该说能够联系到我们的这个几位专家我们也非常乐意跟大家一起讨论一些新的问题。再次呢非常感谢感谢 Nancy， 感谢 Francisco， 感谢这个镍协会木协会给我们的这个这么大的支持
Thank you very much.
好，谢谢大家，
Thank you,
谢谢大家，
everyone.
今天晚上就到这里。
Bye.
谢谢各位